Hello everyone, welcome back to another video from IB Tutoring. In this video we will be discussing complex numbers. Now, what is a complex number? A complex number is defined as a number in the form of a plus bi, with a being the real part of the number and bi being the imaginary part of the number. Please note that I is defined as the square root of -1, which should be an impossible number in theory, as you cannot square root negative numbers. Now, we're going to have an exercise here to determine what is the actual complex number. So, for our first example, we have 3 minus 4i plus 16 plus 6i. What would the complex number be? If you said 19 plus 2i, with 19 being the real part and 2i being the imaginary part, you are right. So we'll put the a for the real part to be 19 and the 2 for the imaginary part to be 2. Now for our second exercise, I think you all understand what this is. I'll give you a moment to think. So the complex number would be -10i, and this is referred to as purely imaginary, as there is no real element to it. So the a will be 0, you can see its coefficient is 0, and b will be -10. So now we can see all of these numbers are purely real numbers since they don't have a coefficient I, and all these are imaginary because they do have a coefficient I. Now, complex numbers can be written in many different forms, and we're going to start off with the most basic form, which is referred to as the general form. We say z is equal to a plus bi, with a being the real part, refers to as re in brackets z is equal to a, which basically denotes that the real part of the complex number c is a, and we refer to the imaginary number as im bracket c is equal to b, which states that b is the imaginary part of the complex number z. The general form simply states that the complex number c is equal to the real part plus the imaginary part. Now, what is a conjugate? You can derive a conjugate from a complex numbers. What is a conjugate? You can derive a conjugate from a complex numbers general form. And simply, all that a conjugate really is the reversal of the sign of the imaginary part of the complex number. So, if the complex number is a plus bi, it will turn into a minus bi. Or, in our example, if the complex number is 10 plus 18i, it will turn to 10 minus 18i. Now on to our next section, the sum of two squares. You may have already heard of the difference of two squares, which is very common in algebra. So let's take our example of x squared minus 81 is equal to x plus 9 times x minus 9. That is a very simple and straightforward sum of two squares, where 81 being 9 squared and x squared is used. Now, what is the sum of two squares? Since I squared is equal to the square root of -1 squared, I squared is also equal to -1. So, if you have I squared present in the negative number of a square root, you will obtain a sum of square roots, since the I squared will cancel out the negative sign using this property of I, we can rewrite a squared plus b squared to be a squared minus b squared times I squared. And in this way, we can take a sum of two squares and transform it into the difference of two squares using complex numbers, using these steps. Now, you can also notice that in both terms that result from the sum of two squares are conjugates. Here are some examples of some factorizations. You can take a moment to look at it. I would recommend pausing the video if you don't understand it straight away. Now, keep in mind that all mathematical operations stay the same in the complex number universe. So, if you're adding one complex number to another, you'll get two complex numbers. Or, if you're multiplying a complex number by another, you'll get its multiplication. We can see a better explanation here. Now, here's a tip when you see complex numbers in fractions. If you see a complex number in the denominator of a fraction, you can simply multiply it by its conjugate to obtain a real number in the denominator, which will make it much easier to make mathematical operations with that number. Now, let's move on to the equality of complex numbers. Two complex numbers are only equal when their real parts are equal and when their imaginary parts are equal. So, if you want to check that two complex numbers are equal, you have to first check that both of their real numbers are equal, and then check that their imaginary parts are also equal. It cannot be a combination. So now, I have a little exercise for you, where you can check if these complex numbers are equal or not. For part A, lock in your answers. And yes, if you said they're equal, you are correct. Because once you simplify the left-hand side, you will get the right-hand side, which means they are equal. Now let's look at part B. Lock in your answers now. And yes, once again, they are equal because of the sum of two squares. Now let's look at part 3, or part C. If you said that they are not equal, you are correct, because once you simplify on the left-hand side, you will get 22i, which is incorrect from the 20i on the right-hand side. Let's look at D. Lock in your answers now. If you said they are not equal, you would be correct, because on the left-hand side, it will be 12 plus 10i instead of 12i plus 10. I mixed it up a bit to trick you guys up. And now for E, lock in your answers now. And yes, they will be equal, because once you expand the squared bracket, you will get that result. Here's an explanation of all the steps taken to find the results. So we can see on the left-hand side, our A will be 4 and our B will be 1, which is correct up here, as it is also 4 and 1. Now, if we look at the result here, our A will be 0, since now if we look at B, our A will be 17 and our B will be 0. And if we look at our comparison here, once again, our A is 17 and our B is 0. Now if we look at C, after a simple simplification, it is just swapped up. So our A is actually negative 33 and our B is 22. But if you look here, in this case, our A is negative 33 and our B is 20. And as you can see, these B's are not equal. Moving on to D. After simplification, we get 12 plus 10i, so our A is 12 and our B is 10. But then if you look over here, then our A is 12 and our B is 10. But if we look at what we are comparing to here, then our A is 10 and our B is 12. And here, after we expand, we'll get this. And you have to keep in mind that the I squared turns into a negative 1, which will be subtracted from the 25, turning it into a 24, which will give us an A of 24 and a B of 10. And if we compare, then it is correct. Let's move on to the properties of the conjugates of a complex number. So, if you take the conjugate of a conjugate, you will get the original complex number. If you take two complex numbers and put a conjugate around a bracket around both of them, once you expand the bracket, both numbers will be conjugates. And this is also the case if you subtract a complex number from another within the bracket. Similarly, if two complex numbers are multiplied within a bracket, and then you expand the bracket, they will both be conjugates, and that goes the same for factorization. Now, we will be proving these two properties since they are a bit more difficult. So now, we will prove that for C to the power of n, so for any complex number to the power of n, conjugated is the same as any complex number conjugated to the power of n. So let's take the example of C to the power of 2's conjugate. We can see that C to the power of 2's conjugate will be negative 2i. So this number will not have a real value. Now, let's check for Z conjugate to the power of 2. This should give the same result. And if you can see from this explanation, it does. Now, let's check for Z to the power of 3. For Z to the power of 3, it also gives a negative 2 minus 2i. Now, for Z conjugate to the power of 3, it should give the same result. And after some simplification, it does. And there's actually no need to repeat further than this, because after these two steps, it will begin to repeat in a predictable way. Now, we have to prove that Z plus Z's conjugate is always real. This is very easy, as you can see that Z's, and this is very easy to prove, as you can see that the complex number Z's imaginary part and its conjugate will always cancel out, giving us the real part times 2. And now we also have to prove for Z times Z's conjugate to be real. And you can see through this small simplification that it will also always be true, as the I will be cancelled out, and so nothing will have coefficient I, so it will be a purely real number. Now, if you completed algebra, you will notice. Now, if you completed algebra, you will know that there are some quadratic formulas that cannot be solved. For example, when the square root is negative. Well, now that we know the power of complex numbers, we can actually go past this and always solve quadratic formulas, as we now know that we can go into the negatives in a square root. But now we can say that quadratic has imaginary roots. Now, you may be wondering, you can show x and y on a graph, but how can you show imaginary numbers on a graph? Can you do this? And the answer is yes, on a complex plane, which is very different from the Cartesian plane, which you may be used to seeing. Here, we can see that our general form, here you'll be able to see how our general form is used to display complex numbers on the complex plane. So here, our task will be to draw 8 plus 4i, 8 minus 4i, minus 4, and 2i on a complex plane. So first, we'll have to draw out our plane. And what you will usually have the y-axis, you will have the imaginary axis denoted by an I. And on the real axis, and for the x-axis, which used to be our real axis, we will have the letter R. Let's say that 4 of these will be 8, just like that. And these two will be, of course, 4. And our real axis and our x-axis will be known as the real axis. And it will be denoted by an R. On the real axis, all the real parts of our complex numbers will lie, and on the I-axis, or the imaginary axis, all our imaginary parts will lie. So this will be 4i here, and then this will be simply a 4. And then here it'll be an 8, and each square will count for 2 units. So to show 8 plus 4i, we go 8 positive in the real axis and go up 4i. And we'll reach here. Next, we do 8 minus 4i. So we go to the right 8, and we go down 4 imaginary numbers, which will lead us here. Then we have to represent negative 4, and this will be right here as we go to the left 4 units, and we will also have 2i, where we go up 2 imaginary units, so it'll be right here. Now, you'll notice that if you connect the origin point, or the 0, to the complex number, you will get a vector, but more on that later on. Now, if you connect these, you'll notice that it's a vector. And with these complex number vectors, we can do some interesting things. In the vectors chapter, you should have seen some vector operations. And if you didn't, don't worry. We have a video with that very soon. So, addition and subtraction with vectors will remain the same for complex numbers. So, if we define z1 to be 2 plus I, and z2 to be negative 3 minus 2i, we will have 2 plus I plus negative 3 minus 2i, which will give us negative 1 minus I. And representing this on the plane, we will go like this. Now, if we have z1 plus 2, z2 conjugate, we'll have 2 plus I plus 2, negative 3. But this case, it will be plus 2i. Since it's its conjugate, we will get 4. We will get negative 2 plus 5i. And that will be here and here. Now, if we just get C1 plus the conjugate of C1, you may remember that it is 2a, which is equal to 4. So it will simply go like this. Now, if you remember from your vectors chapter, each vector has a magnitude and a direction. That is what makes it a vector. For complex numbers, the magnitude and the direction still remains, but it does not come under the general form, but rather under another form, which we will soon see. If we look at this vector here, now, a magnitude in the vectors chapter, the length of the vector was referred to as the magnitude, and the angle was referred to as the direction. In complex numbers, we have different words, but they essentially mean the same thing. We have the word modulus, which will be the same as the magnitude and is denoted as the absolute value of c, but it really just means the magnitude. And the argument, which is its direction. Now, how do you calculate the modulus? How do you calculate the hyperbola of a right-angled triangle? Pretty simple. Pythagoras. So for our complex number here, we will have a modulus of square root of 2. How do you calculate the argument? Again, if we use trigonometry or the tangent with this specific domain, we will get pi over 4. Now, it is important to note that purely real numbers will only have argument 0 and pi, and imaginary numbers will only have pi over 2 and minus pi over 2. That is because they are stuck to either the real axis or the imaginary axis. Always keep in mind the domain of the argument. This domain can never be changed, and you always must keep it in mind for complex number equations. Here are a few properties of the modulus. They're pretty rudimentary and straightforward, but you can pause and take a look at them nevertheless. And here are some revision formulas for geometric equations. So, if you want to calculate the midpoint of two complex numbers w and c, it will just be w plus c over 2, and the distance between them will be simply w minus c under the modulus sign. The introduction of the modulus and argument leads us to our next form, which is known as the polar form, and is most commonly used when actually talking about complex numbers as vectors. The polar form is the modulus of a complex number times cis of theta. Now, what is cis? Cis is defined as cos theta plus I sine theta, and you will see a lot of this as you go on with complex numbers. Keep in mind that the argument of the complex number z Keep in mind that when you find the conjugate of the complex number c, the only thing that changes in the polar form is that its angle turns negative or switches signs. Now, here is a short challenge for you using trigonometry and Pythagoras theorem. Try to write the following equations or convert the following equations from general form to polar form. Take a minute to pause the screen if you need. I will be revealing the answers shortly. Okay, 3, 2, 1. For our first number, we have 2 square root 2 cis pi over 4. For our second number, it's the square root of 41 cis of 0.67. For our third complex number, for our fourth complex number, we have this. Keep in mind that it is in radians. Now, how do we represent the polar form on a diagram? Is it the same as the general form? In fact, no. Now that we introduced theta and angles, we can represent this on a unit circle, with the radius of the unit circle being the magnitude or modulus of the vector of the complex number. And here we have a quick conversion from our complex number in polar form to general form. So you can see it is possible to convert it in both ways. Here are some interesting properties of cis. When you multiply two cis numbers, when you multiply two cis numbers, the angles will add up. When you multiply two cis numbers, the angles will add up. If you divide them, they will subtract. And for cis theta plus k2 pi and cis theta plus 2 pi will repeat infinitely, as 2 pi is a full rotation of cis and will end up on the same point. Here is a short example. Cis of 15 pi is equal to cis pi plus 7 times 2 pi, which is only equal to cis pi. Here is an example of a multiplication of complex numbers in polar form. So, as you can see, the modulus multiplies and the argument adds in a complex number multiplication. Here is a tip you can use in your exams. You can actually use the cis form to split surds in trigonometry. So, if you have cosine 7 over 12 pi plus sine 7 over 12 pi, you can just turn it into cis 7 over 12 pi and then split it up and then use the sys property of being able to, create this multiplication to create sys 1/4 pi plus times sys 1/3 pi. Here, next we move on to the third, final, and also most useless form, the Euler's form. Next, we move on to the third and final form of complex numbers, the Euler's form, which is denoted as modulus of z times e to the power of I theta. And I and e to the power of I theta is defined as cos theta plus I sine theta. So sys of theta is actually equal to e to the power of I theta, which is quite interesting. The polar form allows us to calculate exponents easily through de Moivre's theorem. Let's take this example here. If we take the complex number z in its base form, we have this result here. If we bring it to the power of 2, we can easily multiply it. We can easily multiply its modulus and add its argument, and we get this result here. And this is very easy to predict, very easy to denote. And this is known as de Moivre's theorem. And it can be written as, in a general form, the modulus of z to the power of n times sys n theta is equal to the complex number z to the power of n. Let's move on to the roots of complex numbers. We have this very simple looking equation here, with the complex number z to the power of n is equal to c, which is just a complex number. N here denotes the number of solution or roots to an equation. So, whatever number you have, its highest exponent will be the number of solutions you have. There will always be exactly n roots, and if c is a real number, the complex roots will all be conjugates of one another, because of course they have to cancel out, and if they don't cancel out, it will not be real. If c is not a real number, the complex numbers can have some conjugates, but are not required to be conjugates. All roots will have the same modulus, all roots will have the same modulus, which is the modulus of c to the power of 1 over n, which is very interesting. And on an Argand diagram, the roots will all lie on a circle, and all roots are equally spaced on a circle. So, if you know how many roots there are, if you know the spacing between the roots, then you can find all the roots simply using this theory. This is known as the nth roots method, which is also the best way of finding the roots of a complex number. So, if you use your normal method, which you may have been doing before finding out about complex numbers, you could have taken a number such as x to the power of 3 is equal to negative 27, cube root it, and only found one solution of negative 3. If we introduce complex numbers, then we can just then we can refer to x as z, times it by negative 1, or sys times it by negative 1, or sys. If we use the nth roots method, a complex number method, we turn the x to a z cubed, and then we times it by negative 1, or sys, open brackets, pi plus 2k pi. After this, it is easy to use De Mor's theorem to simplify this by dividing what we have inside by 3 and cube rooting our modulus by 3. And we have this very simple solution here. And we have this k number here, which will actually give us all of our solutions. So we just go through each k value one by one, starting at 0. When k is equal to 0, we'll have 3 cis pi over 3. When k is equal to 1, we will have 3 cis pi, and cis pi is simply equal to -1. And when c is equal, and when k is equal to 2, c is equal to 3 cis 5 pi over 3, which will be our 3 results. And if you go to k is equal to 4, you will notice that the results will be equal to one another. And this will give us our 3 roots. Our last note is that the nth roots of unity are the solutions of Cn is equal to 1. This is just a matter of notation. It is good to know. Now, we're going to move on to the bonus segment of this video, where I will share with you some calculator tips and some exam tips. The calculator tips will be for the TI Nspire graphing calculator, which should be the standard. If you click menu, then go to number, then go to complex, you will find all the different, if you go to menu, if you go to number and then complex, you'll find a very nice list of possible calculations to do with complex numbers, such as finding the real part, finding the imaginary part, and more. If you are wondering where to find something, maybe you should click this button and it will reveal with you the modulus symbol, which will help you find the modulus of a complex number. And now we can move on to the exam tips, and based on past papers, there are a couple common types of problems that include complex numbers. For the paper 1, it is questions where you consider equations have some roots and you have to find some missing information. And to do this, you have to know root theorems very well. And I really recommend learning this root theorem. So for paper 1 questions, we'll have questions where you consider the equation, have some information, but not have all of it, and then just go on from there. All these questions are similar, and for all of this, you have to know the root theorems. You have to know how to find the roots of complex numbers very well. You have to be very solid on that. The next type of question, you will get 2 complex numbers, and you will have to find out the missing value. You just have to know how to place complex numbers in a system of equation. Keep in mind all the tricks in which I squared is equal to -1. Of course, there will be the simple questions of finding the argument or the modulus, or just complex mathematical equations using complex numbers. For that, you just have to be aware of a twist, such as expressing it in terms of something, but if you're strong on algebra, it should be fine. There will be questions where they just ask you to use De Mor's or the nth roots theorem, or plotting points on the Argand diagram, or finding the real and imaginary part, of course for the part B of a paper 1 as a small part of the question. For the paper 2, again, for the smaller questions, you'll be asked to find the modulus, the argument, or the minimum value, or to prove something, or again to find a system of equations for which you will have to use your calculator, or again just to show, and you just have to use your calculator wisely to prove that a complex number will fit a certain standard. Thank you for watching the video. I hope you enjoyed. This has been IB Tutoring. Thank you.